Okay, so I think pwede tayo siguro magsimula para medyo ano din tayo, medyo matapos din tayo ng ano. If ever, marami-rami tayong mag-discuss ngayon. Although for today naman din kasi I'll be letting you watch recorded lecture. Okay, so may ni-record akong lecture. Bali, yun yung papanood ko sa inyo as part ng discussion natin for today. Okay. Although feeling ko pagkatapos nung recorded lecture na mapapanood niyo, may konti pa tayong oras. So baka meron akong idagdag na discussion. Okay. So ayun, pinili kong mag-record na lang ng lecture sa inyo kasi medyo hindi na talaga kinakaya ng hindi na talaga kinakaya ng PC ko yung pagsabayin yung MATLAB tsaka Teams. So para medyo mas efficient tayo sa discussion, ayun. Nire-record ko na lang. Okay. Tapos just a reminder, okay. So mamaya yung hindi, wala pala kayong homework ngayon. So pero tomorrow would be your quiz number 4. Okay. So kine-check ko kung ano yung sakop ng quiz number 4 ninyo. Pero tama ba na ang quiz number 4 ninyo is all about root locus na lang? Tama ba yun? Kasi parang naalala ko yung quiz number 3 ninyo about stability tsaka steady state error. So naisip ko baka yung quiz number 4 ninyo is all about root locus tsaka ito hanggang dito sa discussion ito. Ayun, alam ko, yan tama. Ang quiz number 4 ninyo, ang quiz number 3 ninyo, ang pinakadulo ay steady state error with disturbance. So tama. So tama, ang quiz number 4 ninyo is all about root locus, no? So i-expect nyo na medyo mas konti yung number of questions na may encounter nyo for tomorrow's quiz. So baka medyo late kayo magsimula ng quiz. Baka simulan natin to ng mga around 3 o'clock. Okay, baka mga 3 o'clock na to. Kasi dati mga 10 items yung binibigay sa inyo. Baka ngayon mga mga 4 or 5 or 6 items lang. Yun yung iano ko sa inyo. Okay. So anyway, kung if I see the need naman to start the quiz earlier, I'll start the quiz earlier at 11 pa rin. Okay. So announce ko na lang. Okay, later. Kasi pinag-isipan ko rin na baka mas konti yung number of items. So baka mas okay na mas konti rin yung time na sakupin ng quiz. Okay. Tapos hindi pa rin kasi ako tapos dun sa lab assessment. Supposedly dapat kahapon or ngayon na-post ko na siya. Pero hindi pa ako tapos. So ayun, pakihintay-hintay na lang. But anyway, for today, we'll discuss design via root locus. Okay. May nilagay na akong lecture sa ninyo, sa content library ng class notebook ninyo. Okay, so paki-check na lang. Pero may kulang pa 'yon. So i-update ko na lang later. Okay, so may isa pang kulang na article dito, basically. So update ko na lang 'yan later. Together with a recorded lecture. Okay. So just a reminder na ngayon, quiz number 4 nyo ngayon. Tapos, kailan ng final exams niyo? Kailan ko ini-schedule? Pero kailan ko siya ibibigay? 19 yung deadline, yeah. Naalala ko 19 yung deadline. Pero kailan ko siya ibibigay? Sunday or Monday? Monday. Monday yan, no? Sunday by 15? Sunday. Okay. So, sige. 19 is Thursday. 15, 16, 17, 18, 19. Okay, sige. 5 days. Okay. So, Sunday. So, Sunday ito bibigay. Deadline natin is 19. Okay. Tapos, yung sa laboratory ninyo, paintay na lang. Medyo hindi ko pa siya natatapos eh. Okay. So, sige. Ayun. So for today, discuss natin tong design via root locus. Pero this time, gumawa na lang ako ng recording para mag-discuss para sa inyo. Okay, so I hope you listen in. Okay, so wala tong masyadong interaction kasi recorded lecture to. Okay, so pero I'll hope you listen in pa rin. Okay, so paki-advise na ako pag walang audio. Okay, so sige. Okay. So now that we that we have been we were able to discuss now. Wait lang, may audio ba? May audio yung video. Okay, so sige. Yung root locus ninyo. Okay. We will not be able to use this tool as a means of coming up with a controller design para ma-meet natin yung transient response and steady state error requirements while we ensure that the system is stable. Okay? So in the previous lesson, okay, nakita natin that we can actually come up with a decent design of your controller. Kaya lang, since we are just merely adjusting the gain, okay, it also means that we are only working along the root locus only. Okay, and therefore, our improvement would be limited to those points that are on the root locus. Okay, but then if we would want some more flexibility. Okay, if we would like to be more flexible, okay, in terms of meeting your requirements, okay, both in terms of transient response and steady state error, then we would need to be able to reshape. Okay, there is a requirement for us to be able to reshape the root locus, and that is accomplished by adding poles and zeros to the system. Okay, so this chapter will demonstrate how are we able to do this. Okay, how are we able to design these compensators so that we can meet these requirements. So yung made-design nating yung made-design nating compensators or controllers, okay, are basically either passive controllers or active controllers. Okay, so remember lang na when we talking about your system, again, yung ating general topology would be something like this one. Okay, so yan. Okay, so this is your input R, this is your output, say Y. Okay, now this is your F, your input transducer F. This is your plant G. Okay, this is your feedback H. And this would be your controller C. Ito yung i-design natin. Okay, we would need to come up with a design of the transfer function for this C so that we would be able to meet your transfer function, your transient response and steady state error characteristics. Okay. Now, there are two ways to design this controller. So yung una nga is yung we will be using passive networks to do this. Okay, or we will be using active networks. Okay, so basically sa konteksto ng pinag-aaralan natin, itong C na to is basically itong controller natin to is basically an electrical network. This would eventually boil down to an electrical network. Okay, so dahil nga yung H natin would be the sensor, F would be a converter that would convert the input to an electrical signal, and our G is basically your plant or your process, okay, which may be mechanical, okay, or electromechanical or pneumatic or whatever system, okay. So yung C natin is basically an electronic circuit. Ang controller natin or ang compensator natin is an electronic circuit, okay, which can either be passive or active. Okay. Now, dalawa yung approach na gagawin natin dito. Okay, so kapag active, okay, we'll be coming up with a what we call a proportional integral derivative controller or compensator para sa ating controller. Okay, so yung itong PID controller natin would be using active circuits. It means it would be implemented using an op-amp. Okay, so ayan. Now, if your controller naman is chosen to be passive, it's it would be a lead lag it would be a lead lag circuit, okay, which would comprise mostly of it would just mostly be composed of passive networks. Okay, so yun yung tinitingnan natin dito. Okay, so at the end of this lesson, you must be able to use the root locus to design cascade compensators to improve the steady state error. Okay, use the root locus to design cascade compensators to improve the transient response. Use the root locus to design cascade compensators to improve both the steady state error and the transient response, and to realize the design compensators physically. Okay, so there. Now, the root locus would typically allow us to choose the proper loop gain, okay, to meet a transient response specification. Okay, so as we ayun nga, the root locus would allow us to meet a transient response specification. Okay, so adjusting your gain along the root locus would give you the proper gain para makuha nyo yung tamang transient response na gusto natin. Okay, however, setting the gain at a particular value yields a transient response dictated by the poles at that point on the root locus. Okay, so kung gusto nating iset yung ating transient response sa ibang parte ng ating S-plane, okay, o sa ibang we would be only limited, we would not be able to do that, na ma-set natin yung ating operating point, or may set natin yung ating closed loop poles sa isang point na wala dun sa root locus. So therefore, limited lang tayo dun sa root locus natin mismo. Okay? So, for example, kung titingnan natin tong ating improvement in the transient response. Okay, we will have the following. Or we can see the following. Okay. Halimbawa, may gusto tayong i-meet. Say for example, settling time, okay, or peak time. Okay. Now, if your pole, okay, or if at a certain gain, okay, nandito yung location ng pole niyo. Okay, if at a certain value of gain, nandito yung location ng pole niyo. Okay, remember lang na yung close to pole niyo. Okay, remember lang that you would only be limited by you would only be limited in setting your gain along this root locus. Okay, so halimbawa ngayon na gusto ninyong ngayong say for example, mag-meet ng certain TS or TP requirement yung inyong system. Okay, then you would be changing your overshoot kasi magbabago this line actually sets that or along this line your overshoot is constant, or your overshoot is basically constant. Okay, pero once na gusto nyo, say for example, i-meet yung TS or TP, take note that TS is basically 4 over sigma t, or the real part of your pole or of your closed loop pole, and TP is basically pi over the imaginary part of your pole. So kung iibahin nyo either TS or TP, take note na iibahin nyo yung real part or imaginary part ng pole niyo. Okay, so that means you either move towards here o kaya towards here. Okay, and if you see na we would just be moving along this root locus, then definitely may iba yung location of the outline niyo. Okay, Now, what if we want to what if we want to meet a certain TS or TP requirement, but at the same time we want to make our overshoot essentially the same. Okay, with the original original uncompensated system. Okay. So kung wala pang compensation or hindi pa natin na-design yung compensator na system niyo, it has a certain overshoot. Then kapag nagkaroon na siya ng compensator, mamimit natin yung TS and at the same time, mapapanatili natin na constant yung overshoot niyo. Okay? That would require you to move your pole from here to here. Okay? To a point somewhere here. Okay? Which now, obviously, wala na sa root locus natin. Okay? So therefore, kapag ganyan yung kanya kailangan niya. Okay? Yan, for example, kung titingnan niyo to, in this case, there is an improvement in TS kasi ito yung TS nung sa A. Pero yung sa B, okay, nandito yung TS niyan. So nag-improve yung TS niyan, bumilis yung settling time. Okay, pero makikita nyo na yung kanyang overshoot, halos pareho lang. Okay, it is possible by moving from point A to point B. Okay, but again, as you can see, point B is not on the root locus. Okay, so paano natin ngayon mamimit yung ganong requirements that we improve TS but at the same time we maintain the overshoot. Okay, so in that case, what we will do is we would need to have your root locus reshape. Kailangan mabago natin yung shape ng root locus natin. And then, when we reshape your root locus, we would make that root locus pass through that point B. Okay, so hindi lang basta reshape. Pag ni-reshape natin siya, dapat yung root locus nyo dumaan din sa yung bago yung root locus na ni-reshape no, dumaan sa point B. Okay? And how do we do that? Okay, how do we reshape the root locus and then make the root locus pass through a certain point? Okay. By the way, tatawagin natin tong point B as the new operating point. Okay, and itong point A as the old operating point. Okay. So instead actually we can also call that as the complex dominant pole. Pero para mas suggestive siya or para mas intuitive siya, okay, we will call those operating points where your system is said to be operating on. Okay. So basically that's the closed loop pole that your system operates on. So that mamimit niya ang certain, say for example, overshoot or certain damping ratio. Okay. And then i-redesign natin yung controller natin such that yung operating point na yan, magagalaw natin into a new operating point that would meet our requirements. Okay? So how do we then, babalik tayo sa question natin. How do we then move or how do we then reshape this root locus and at the same time make the root locus pass through a new operating point? Okay? So what we do is we augment. Okay? We augment or compensate, okay, the system with additional poles and zeros. Okay? So what we will do is we will add open loop poles and open loop zeros sa ating system. Okay? So yung open loop poles at saka open loop zeros na yun, doon manggagaling yun sa controller natin. Basically yung controller nyo, okay, say for example, you have yung transfer function ng controller nyo, aside from the gain, meron din siyang compensator zero at saka compensator pole. Okay? So, ayan, idadagdag natin to dun sa, ito yung controller niyo. Yan yung multiply dun sa G, which itself has its own open loop poles and open loop zero. So, yung compensator zero tsaka compensator pole natin would actually augment yung open loop poles and zeros ng G. Okay? Which in turn would actually reshape your root locus and would actually force your root locus to pass through a certain operating point that we desire. Okay? So, yun yung approach na gagawin natin to be able to improve the transient response and the transient response. Okay? So there. Now, how about the steady state error? Ang steady state error, basically, isang way of actually improving your steady state error is increasing the system type. Okay? Take note na halimbawa, if your system is a type 0 system, okay? So halimbawa meron kang K over S plus 1 times S plus 2. Okay? If you have this system na type 0, okay? So alam natin na meron yang error sa step input. Okay? So kung gusto nating ma-zero yung ating system or yung error natin or yung steady state error natin due to a step input, what we want to do is to increase, okay, the system type of this. Gusto natin siyang gawing type 1 para magkaroon siya ng integration factor dito. And thus, ito, magiging 0. Kasi yung kanyang KP, okay, mag-i-increase yan up to infinity. Okay? So, yung improvement na yun, okay, can actually be done by adding an integration factor doon sa inyong forward transfer function. So ito, ang mangyayari ngayon dyan is that yung ating controller, meron na siyang gain, tapos meron pa siyang integrator. Okay? Tapos ito ngayon yung G niyo is 1 over S plus 1 times S plus 2. Okay, which would be your forward transfer function. So from there, makita natin na yung system type niyo mag-i-increase from type 0 papuntang type 1. And therefore, that would render your steady state error to a step input to be 0. Okay? Also, kung hindi naman siya 0, okay? Kung hindi naman siya 0, I mean, hindi naman natin talaga target na maging 0 ito, pero we just want to have some kind of improvement. Okay? Ang tandaan natin is that we want to increase KP. Okay? When you increase KP by a certain, or your static error constant in general, by a certain factor, you would be able to see na magkakaroon din ng dramatic decrease sa error. Okay? Take note na ang ating error due to the step input is basically 1 over or A over 1 plus KP. So that kapag in-increase natin si KP, alam natin bababa si steady state error. Okay? So that would be accomplished. Okay? That can be accomplished by adding A0, okay, and a compensator pole, okay, doon sa ating controller. Okay? And then making sure na yung ratio ng ZC over PC. Okay, yung ratio na to. Okay, yung ratio ng ZC over PC would actually be greater than 1. Kasi kapag kinumpute natin yung error or kinumpute natin yung say for example, meron na tayong forward transfer function na K times say S plus CZ, okay, over S plus PC times S plus 1 times S plus 2. Okay. Pag kinumpute nyo yung KP nito, okay. Pag kinumpute nyo yung KP niya, that basically is K times CC over PC times 1 times 2. Okay. So kung yung ratio na CC over PC natin is actually greater than 1, then we can expect an improvement in KP and therefore an improvement in the steady state error performance of your system. Now, what's a good thing is that mako-control natin kung nasan tong ZC at saka PC natin so that hindi lang natin siya may state as greater than 1. But actually, we can actually set yung value na yan. Itong value na to. For example, kung gusto natin ng 10-fold improvement in terms of the steady state error or in terms of the static error constant, then we can set CC over PC to be equal to 10. Kung gusto natin ng 10-fold reduction, 10-fold improvement in the static error constant. Okay? So kung 10 yung isa-set natin para dyan, then we can choose a location for your compensator 0 at compensator pole para maging 10 yung ratio na yan. And therefore, pag kinumpute natin yung KP, there would be a 10 times improvement in the KP. Okay? And of course, in terms ng KP at saka ng steady state error for the step input, hindi kasi exactly sila proportional. dahil merong 1 na factor dito. Okay? So, parang halimbawa, in terms of unit step, yung 10 times yung 10 times improvement sa KP would actually translate to around 1/11 na reduction sa error. Okay? So, hindi sila exactly proportional. I mean, proportional sila pero hindi sila exactly parehong value. Hindi katulad niyan na kapag ka KV at saka yung steady state error due to ramp, kung ito i-improve mo by 10 times, mag-reduce din to ng 10 times. Okay? Kasi sila, yung formula nila is basically ang ating steady state error due to the ramp input is basically 1/KB. So pag ito in-increase mo by 10, ito magde-decrease by 10. Okay. Same thing with the parabolic boot and the KA. Okay, pero sa KP kasi iba yung usapan dahil merong extrang 1 na factor doon. Okay, pero more or less medyo mape-predict natin na pag tinaas mo si KP, bababa si error. Okay? So, that is how we improve the steady state error. That is, either we introduce integration factor so that we can reduce the error to 0, o kaya we can introduce poles and zeros, okay, or compensator poles and zeros para makita natin na ma-achieve natin yung improvement sa static error constant na kailangan natin. So yung mga techniques na yun will actually be discussed in the next sections. Okay, nung ating chapter na to. Okay. Now, so as I was saying kanina, okay. Yung configuration, mahalaga na magkasundo tayo dun sa configuration nung ating system na gustong i-compensate. Okay? So actually merong various techniques of doing of compensation techniques, okay, na available. Yung isa is yung cascade compensation na tinatawag, okay, in which yung compensator ninyo is basically naka-cascade or naka-series dun sa ating plant. Okay. The other one is that tinatawag na feedback compensation, okay, in which yung compensator ninyo is ilalagay natin dun sa feedback. Okay? Sa feedback loop. Okay? With cascade compensation, the compensating network, okay, is placed at the low power end of the forward path in cascade with the plant. Okay, so that is why yung compensator mo actually requires a low power or it has low power requirements. Okay, kasi yung compensator mo hindi mo nilalagay doon sa pwesto nung or doon sa part nung system mo that actually requires high power na, for example, nire-require nung system ng plant mo such as motor, okay, or a hydraulic system na mataas yung power. So ilalagay natin siya dun sa low end power nung system natin. Okay, that is why we will design this controllers using electronic circuits. Kasi nga hindi naman malaki yung requirement nila pagdating sa power. Okay, ang kailangan na nila is magbato ng signal dun sa inyong plant. Okay, in which that signal would actually cause your plant to react in a certain manner. Okay, and therefore would be responding to that signal. Okay, depende dun sa level niya. Okay, depende dun sa level ng signal na yun na ibabato dun sa plant niya. Okay. Now, in this lesson, okay, we will be limiting ourselves to cascade compensation techniques. Okay, so limited lang tayo dun sa cascade compensation techniques. Okay, and again, paulit-ulit ko na sinasabi sa inyo ito, yung tungkol sa topology na gagamitin natin. So again, we will be using yung topology na pinakita ko sa inyo before pa, okay, in which ang i-design natin doon is yung compensator na nasa tabi ng ating plant. Okay? Now, compensators. Compensators that use pure integration for improving steady state error or pure differentiation for improving transient response are defined as ideal compensators. Okay, so pwede natin gamitin yung ating pure integrator, okay, or yung ating integrator at yung ating differentiator, okay, to be able to improve steady state error para sa integration or integrator at saka transient response para sa differentiator. Okay. But these compensators are only implemented using active networks. Okay. Yung ating integrator, okay, yung 1/s natin na system at saka yung ating differentiator, okay, yan ay na-i-implement lang in circuit, okay, using active networks. So mai-implement lang natin yan using op-amps. Okay. So other design techniques that preclude the use of active devices for compensation can be adopted. Okay, these compensators, which can be implemented with passive elements such as resistors and capacitors, do not use pure integration and differentiation and are not ideal compensators. So meron tayong pwede naman nating i-implement yung ating compensators using passive elements such as resistors, okay, and which those would not require active elements, okay, such as op-amp, okay, and therefore does not also require its own power supply. Okay, so the choice between an active or passive compensator revolve around cost, weight, desired performance, transfer function, and the interface between the compensator and other hardware. So yan yung ating design consideration kapag mamimili kayo kung active or passive compensators ba yung nire-require ng system niya. Okay? Yeah. Hello, andiyan pa kayo? Ayun. Sige. Okay. Bago ko mag-proceed dun sa next part ng video, gusto ko lang bigyan kayo ng parang pinaka-preview kung ano yung aabangan natin dito sa next lesson natin na to. Okay. So basically, mag-aaral tayo ng design ng anim na mag-aaral tayo ng design ng anim na compensators. Paano i-design yung anim na compensators? Okay. Para medyo may idea din kayo kung saan patungo itong discussion natin. So basically, ang hirap mag-drawing ng straight line sa ayan. Tama ba itong ko? 1, 2, 3, 4, 5, 6. Okay. So, sa una, mag-aaral tayo kung paano i-improve yung steady state error. Masyadong improve steady state error. Okay? Tapos, aaralin natin kung paano mag-improve ng transient response. Okay, and then aaralin natin kung paano mag-improve ng sabay. So improve steady state error plus transient response. Okay, so una, pag in-improve natin yung steady state error, yung transient response basically the same as the uncompensated. Okay? So parang i-improve lang natin talaga yung steady state error. Pero yung transient response, kung ano lang yung original na transient response niya nung wala pa siyang compensation, yun pa rin siya. Okay? Sa improvement naman transient response, wala tayong pakialam kung anong mangyayari sa error. So generally, when you improve the transient response, there must be a certain improvement also in the steady state error performance. magkakaroon din siya ng improvement. Kaya lang, hindi natin kontrolado. Okay, hindi natin controlled kung gaano kalaking improvement sa steady state error yung mangyayari. Okay, pero merong improvement. So, dun sa yung improvement na yun, hindi natin i-design yung improvement na yun. Okay, kapag i-design lang natin is improvement ng transient response. Okay. So huli, i-improve natin sila pareho and in a controlled manner. Ibig sabihin, i-specify natin gaano kalaking improvement sa transient response. Gaano kalaking improvement sa steady state error. And at the same time, ito na yung magiging transient response niya. Ito na yung settling time niya, ito na yung peak time niya, ito na yung overshoot niya. Okay? So, yan yung tatlong tasks natin. Okay? Now, in each of the tasks, magdi-discuss tayo ng dalawang types ng controller or ng compensator na i-design. Yung isa involves the use of active devices. Okay, yung gagamit ng op-amp. Pag dinesign natin into circuits, dinesign natin into an electrical network, gagamit siya ng op-amp. Okay? Tapos, yung isa namang type ng compensator na yan natin is yung passive. Okay? Ito yung purely hindi siya gagamit ng op-amp o kaya pwede siyang gumamit ng op-amp pero yung characteristics niya hindi katulad doon nasa active or hindi ideal yung compensation na magaganap. Okay? Pag sinabi niyo kasing ideal yung compensation, ulitin ko pag sinabi niyo ideal yung compensation, you are able to put in a pure integrator. Okay? Pwede kayo maglagay ng pure integrator o kaya ng pure differentiator. And when you say pure integrator, you are able to put in an open loop pole sa origin. Okay? Pag pure differentiator naman, you are able to put in an open loop zero dun sa origin. Okay? So, yun yung tinatawag nating pure integrator tsaka pure differentiator. At magagawa lang natin yan kung meron tayong active circuit. So, yung ideal compensation can only be achieved via active networks. Okay? Naintindihan yun? Now, if your network or if your compensator does not require the use of integrator or differentiator, okay, pwede natin siyang i-classify under ng passive. Okay? Again, pag hindi gagamit ng ideal integrator or ideal differentiator, yung controller ninyo or yung compensator ninyo, pwede natin siyang i-classify under ng passive. Whether or not gagamit siya ng op-amp. Kasi may mga passive compensators tayo na gumagamit ng op-amp. Okay? Gagamit siya ng op-amp pero hindi siya gagamit ng integrator or differentiator. Okay? So, pwede natin i-classify yun under ng passive. But strictly, i-define natin yung active compensators. Okay? Again, i-define natin yung active compensators are those compensators that uses pure integrator or pure differentiator or both. Okay? Pero kapag hindi siya gumamit ng ganun, okay, pag hindi siya gumamit nito, okay, that compensator can be classified as a passive compensator. Okay? So, ayun. So, I hope malinaw yung part na yun. Now, sa improvement ng steady state error at meron kayong active technique, okay, in the compensation, okay. Tatawagin natin itong proportional integral compensator or PI. Hindi ako nagmumura, PI compensator. Okay? PI is for proportional integral. Okay? So, para ma-improve natin yung steady state error, kailangan natin ng proportional integral compensator kung gusto niyo ng active compensation. Okay? Basically kasi gagamit ito ng integral o ng integrator, ng pure integrator. Okay? So, later on, makikita nyo kung ano yung mga transfer function sa bawat isa. Yung transfer function ng bawat controller or compensator. So, i-take note niyo at gumawa kayo ng same table. Okay? Pag nagsasummarize kayo, gumawa kayo ng same table para makita, at tapos ilagay nyo dito kung ano yung required na transfer function ng bawat controller na to. Okay? So para mas maano siya, para mas maintindihan niyo kung ano yung pinagkaiba-iba nila. Okay? And then mapapansin niyo na meron diyan magkakapareho ng ng transfer function. Okay? Pero it doesn't mean na magkakapareho ng requirements. Okay? For example, meron diyan na magre-require pareho ng compensator 0 at saka compensator pole. Pero magkaiba yung requirement ng compensator 0 at saka compensator pole. Depende sa kung ano yung gusto niyo i-achieve. Okay? Maliwanag 'yun? Okay. So sa improvement ng ng steady state error, meron tayong proportional integral compensator. Kung passive naman yung gusto niyo gawing approach nung pag-i-improve ng steady state error, meron tayong tinatawag na lag compensator. Okay? So may tinatawag tayong lag compensator para sa improvement ng steady state error using passive networks. Okay? Now, sa improvement naman o para ma-improve natin yung transient response, okay? Under active compensation, okay, gagamit tayo ng tinatawag na proportional derivative compensator or PD compensator. Okay? So dito naman ito gumagamit ito ng integrator. I mean ng differentiator. Okay? Gumagamit ito ng pure differentiator para magawa niya yung yung para makuha niya yung improvement sa sa transient response. Okay? While under ng passive approach ng pag-i-improve ng transient response, gagamit tayo or magde-design tayo ng tawag nating lead compensator. Okay? So ayan. Now, para ma-improve natin sila ng sabay, okay, di pagsasamahin lang natin itong dalawang to. For example, para ma-improve natin yung steady state error at transient response, using active differentiation at integration, we will use yung proportional integral derivative or yung PID compensation or PID controller. Okay, so pagsasamahin natin itong dalawang to. Okay? Sa passive naman, under the passive approach, we will use yung tinatawag na lead lag compensation or compensator. Okay? So, in this sa mga susunod na yan yung aaralan natin. Paano natin i-design yung anim na yan? Okay? So, once na maaral natin kung paano i-design yung anim na yan, okay, we will now be able to to design controllers para sa system natin para ma-achieve natin yung certain level ng transient response or certain level ng steady state error na gusto natin para sa system natin. Okay? And in all of this, pag inaral natin yung anim na yan, gagamit tayo ng root locus para ma-accomplish natin or para mas visually mas makita natin kung ano yung nangyayari dun sa system natin. And at the same time, ma-monitor din natin kung yung system natin ay stable pa ba o hindi. Okay? So, again as you study, habang pinag-aaralan niyo to, okay, hindi ko na kasi siya baka hindi ko na siya magawa ng summary, baka makalimutan ko na rin. Pero para habang pinag-aaralan niyo to, I would like you to summarize kung ano-ano yung mga transfer function na kailangan ninyo sa bawat isang controller. Okay, na i-design natin. Okay. Anyway, pag may example naman, babanggitin ko naman kung ano yung kailangan yung transfer function para doon. Okay? Maliwanag to? Okay. Now let us continue. Okay? Tuloy natin siya dun sa sa improving your steady state error. Okay? So, 'yun, magde-design tayo ng PI compensator tsaka ng lag compensator. Okay? So, kinig pa kayo. Now in this section, we will now try to improve the steady state error of feedback system using cascade compensation. Okay. Now, objective natin dito is basically we want to improve the steady state error without changing essentially the transient response. So basically, we will be having a system having an improved error performance, but having the same transient response as the uncompensated system. Okay, so there will be two techniques. Okay, in that we will be discussing here. Okay, so we will first discuss a technique wherein we will reduce the error to zero. Okay, so the first technique would actually reduce the error to zero. And for us to do that, we would be using the ideal integral compensation. Okay? And again, when you say ideal integral compensation, you would use an integrator. Okay? Gagamit tayo ng pure integrator dito. Okay? So as I was pointing out earlier, okay? When you use an integrator, you would be actually increasing the system type of your system. Okay? I-increase natin yung system type. So from a type 0 system, for example, magiging type 1 yan dahil magkakaroon na ng isang integrator dun sa forward path niya. Or madadagdagan ng isang integration factor dun sa forward path niya. Therefore, the system type would actually be increasing. And again, if we have an increased system type, okay, for the same test input, yung error mo, mare-reduce bigla sa zero. Okay, so that's one way of or that's actually a way of reducing your error to zero. But again, the use of integrator would actually require you to use active circuits. Okay, it would require to use active circuit, and therefore, kung hindi amenable or hindi okay sa atin na gumamit ng active circuit, okay, due to say for example cost requirements or power requirements, then we will have another option in which we would not be able to reduce the error to zero, but we will be able to reduce it substantially. Okay, mare-reduce natin siya by a certain factor. Okay, so in that case, what we will do is that we will be using what we call a lag compensator. Okay, so gagamit tayo ng tinatawag na lag compensator. So the lag compensator would actually just improve your error performance but not reduce your error to zero. Okay. Pero one advantage of the lag compensator that it would offer you is that it would only require you to use passive networks para ma-implement siya. Okay, so kung hindi available or prohibitive sa cost ang implementation ng active networks, then you can go with a lag compensator. Okay, the name of the lag compensator actually is stem from from its property pag tinignan niyo yung kanyang frequency response. Okay, so ayun. Another name that we can use for the ideal integral compensator is yung tinatawag nating proportional integral compensator or yung PI compensator. Kung maalala nyo, binanggit ko sa previous section na meron tayong PID or proportional integral derivative compensation. Okay, or controller. Dito, ang gagawin natin is actually isa-isahin natin siya. Proportional integral, proportional derivative, and then yung tatlo, proportional integral derivative. Okay, so yun din yung tawag natin, yun din yung ideal integral compensator natin. Okay, so we will discuss both approaches, itong PI compensation at itong lag compensation, and see how they can actually improve yung ating error performance. Okay, now sa ideal integral compensation or sa PI compensation natin, okay, so the steady state error can be improved by placing an open loop pole at the origin. Okay, basically because it would increase the system type by 1. Okay, and then if you want to retain or if you want to, kasi what would happen is that pag naglagay kayo ng open loop pole sa origin, that would also change the shape of your root locus. Okay, so ngayon para bumalik siya sa dati at para yung root locus ninyo would actually operate on the same operating point that it has before the open loop pole was added at the origin. Then lalagyan natin siya ng open loop 0 na malapit dun sa open loop pole na nilagay niyo sa origin. Okay? So, that would mean na since malapit yung open loop 0 at saka yung open loop pole, basically, magkakaroon yan ng paano yung tawag na pole zero cancellation. Okay, so I'm talking about this one. I'm talking about this this part. Okay, so kung halimbawa na ito yung original operating point niyo or your system operates at that complex pole. Okay. Once na maglagay kayo ng open loop pole sa origin para nga i-increase nyo yung system type, may iba yung shape ng root locus niyo. So ito na yung dinagdag na compensator pole. Okay. So may iba yung shape, mawawala dito sa part na to yung root locus niyo. Okay. So ibig sabihin, may iba na talaga yung performance ng niyo kasama yung transient response. Okay. And again, ang objective nga natin is for us to just correct the error and not change the transient response. Okay. Basically, pabawiin natin yan by actually placing an open loop 0 na malapit dun sa open loop pole na nilagay natin sa origin. Okay. So, kasi kapag naglagay kayo ng 0 na malapit dito, essentially, you are employing yung tinatawag nating pole 0 cancellation. Basically, itong dalawang ito at saka to, cancels each other out. So therefore, sa root locus, hindi masyado mararamdaman yung pagkakaiba yung epekto ng dalawang yan. Kasi nga halos nagka-cancel sila with each other. Therefore, yung shape ng root locus nyo, babalik sa dati. Okay? And then, ma-force ninyo or ma-set ninyo ngayon na yung system ninyo to actually operate back on this point A. Okay? So, for us to be able to design yung ating compensator para sa the transfer function essentially of a PI compensator, okay, or an ideal integrated compensator is that meron kayong gain times S plus JC, okay, divided by S. Okay, so yung ayan, yung sinasabi ko, yan yung transfer function ng isang proportional integral compensator. So i-take note nyo yan. Okay? Kasi later on, kapag sabay-sabay yung dinidesign natin, baka mahirapan na rin kayo hanapin kung nasan yan. So sana meron kayong naka-ready na summary dyan. Okay? Maliwanag yun? Okay, so sige, tuloy natin. S na to represents the open loop pole at the origin. Tapos itong ZC na to must be an open loop 0 that is close to the open loop pole at the origin. Okay, so dapat ito, malapit yung value. So kung ang pole niyo is nasa 0, dapat yung value nito is nasa 0.1 or 0.01. Okay. So the nearer that JC, okay, sa origin, mas malapit yung performance niyo sa yung transient response performance niyo sa uncompensated system. Pero at the same time, yung error niyo is reduced to 0. Okay? So ayun. So we now take a look at an example para makita natin mabuti kung ano yung epekto ng paglalagay ng ideal integral compensator o ng PI compensator sa inyong system. Okay. So first, in this case, gagamit tayo ng CSD app o ng Control Systems Design app ng MATLAB. Okay. So we have this system. Okay, we have this system. We first analyze yung system natin para mahanap natin yung tinatawag nating operating point. Okay. So lagi yun kapag magde-design tayo ng compensator, we always start with the uncompensated system. Okay. Kasi kailangan natin mahanap muna yung tinatawag na operating point. Okay. Yung operating point ng system natin. Okay. So in this case, we would like to find what would be the operating point of this uncompensated system. Okay. So we started with defining your systems sa MATLAB workspace. So yung F natin is 1. Okay, so again, I explained this over and over again before. Okay, so yung f natin is 1, h natin is 1. Okay, then this is your forward transfer function. Okay, so that excludes k kasi yung k ilalagay natin dun sa ating controller design. Okay, so what we will do next is to import this into our CST app. Okay, by choosing edit architecture tapos edit itong edit architecture natin. Now, once this pops out, okay, so again, i-import natin si F. Okay, import natin si F. Import natin si G. Yes, si G, import natin. And then finally, import natin si H. So we press OK, and then we wait for the system to update the architecture. So we now have the following as your root locus of your system. So take note na meron tayong open loop po sa 1 to -1, -2, at saka -10. So we expect na meron tayong tatlong branches. Okay. And then what we would want to do na then is to find the operating point. Okay. Now the operating point is set by the given damping ratio. Okay. So sinabi ng ating problem that we want this system to operate with a damping ratio of 0.174. That means yung complex poles niyo would be along the damping ratio line of 0.174. Okay. So we can set that here by having your design requirements. Okay, right click, tapos design requirements, tapos new. Okay. Then we set na yung ating damping ratio is at 0.174. Press natin enter para pumasok siya. Then click OK. So this is where your yung intersection nitong damping ratio. Okay, this is your damping ratio line, your DR line. Okay. So we would want now to find the operating point. We would like our closed loop pole to be on the damping ratio line. So ang gagawin natin is to set the pole on this DR line. Okay. So ayan. So drag natin siya doon. Ito yung closed loop pole natin, yung kulay pink na dot. Drag natin siya papunta dito. Okay, until it intersects that So ma-check natin yan kapag yung damping ratio natin is nasa 0.174 na. Okay, so let's make sure na talagang intersecting na sila. Okay, so konti na lang. Okay, so let's say yan yung ating intersection na hinahanap. Okay. So let's take note of the current location na sinasabi ng ating Okay. So in this case, ang current location sinasabi ng ating pole or yung current location ng pole natin is at negative 0.694 plus or minus basically 3.93J. Okay. So this might be different dun sa ating nasa lecture natin kasi of course iba yung actual na ginagawa natin and iba rin yung nandito yung nagawa ko na before. So dito kasi nakuha ko siya at negative 0.694 plus or minus 3 a J of 3.92. So ito ay 3.93. Okay. So let us assume na let's assume na I'll be working on this actual yung ginagawa ko ngayon. Okay. So in that case, anyway, konti lang naman yung difference nila. Okay. That's 0. Konti lang naman yung difference nila. Okay. So yeah. So we have it at ipagpareho na natin siya. Okay. So this is negative 0.694. Negative dito kasi naka-positive siya. So let's make this negative. Okay. So this is negative 0.694. Okay, plus or minus J 3.92. Okay, so again, ang damping ratio niya 0.174. Okay. Now, for that location, we take note that the gain, okay, that the gain of your is at 164.44. Okay? So nasa 164.44 yung ating key. Okay? So in that case, we would be able to compute now the static error constant for that. Okay, as 164.44 divided by 1 times 2 times 10. So that gives you at the operating point na meron tayo, which is at this point. Okay. At this operating point. Okay. Or this operating point, bale. Okay. Ang ating static error constant is 8.222. Okay. And the steady state error is computed as 0. Alam ko saan ko kinuha yung formula ng KP. Naintindihan kung paano ko kinompute yung KP para dito? Oh, ayun. Saan ko kinompute yung saan ko kinuha yung formula ng KP? Or in the first place, paano ko nalaman na formula ng KP ang gagamitin ko? Okay. Tapos, pero paano ko muna nalaman na KP yung kukunin ko? Kasi tatlo yun eh. KP, KV, at saka KA. Paano natin nalaman na KP yung kailangan kong kunin? Dahil position yung nag-iba? Di ba in-evaluate ko steady state error? O, di ba? Sabi sa inyo, babalikan natin yung mga dati yung lesson eh. Kaya dapat di nyo kinakalimutan yun. Tingnan natin yung given nyo ha. Yung given nyo ay ito. Ay, wala. Sumabot pala. O, yan yung given ninyo. Okay? Paano from galing dyan, na-determine ko na dapat KP yung kukumpitin ko at hindi KV or KA. Sige. Kung steady state error ang pinag-uusapan natin, paano natin kinakarakterize ang isang system? Or paano siya kinaklasify? In terms ng kanyang steady state error performance. How do we classify systems? Okay? In terms of its steady state error performance. May tatlo tayong may tatlo tayong classification yan. Or ito yung tawag yung system type. So ano yung mga system type na yan? So, meron tayong type 0, type 1, at saka type 2. O, paano natin nalalaman kung alin yung type 0, type 1, saka type 2? Ano yung tinitingnan natin para maklasify natin yung system natin as either type 0, type 1, o type 2? Halimbawa, itong system na to, ano to? Hindi, ito muna. Paano natin muna siya i-classify as type 0, type 1, o type 2? Kasi kapag na-classify na natin siya as type 0, type 1, type 2, tsaka natin malalaman kung ano yung static error constant na associated dun sa system na yun. Yan yung susunod bale. Pero kailangan ko munang malaman. Paano nyo malalaman kung ang system ay type 0, type 1, type 2? Halimbawa, itong given system na to, anong classification ito? Ayun. Patay tayo dyan. Paano natin malalaman kung ito ay type 0, type 1, o type 2? Base dun sa polls? O halimbawa ito, paano nyo masasabi na ano yan? Anong masasabi nyo dyan? Anong classification yan? Yeah, so forward transfer function. Kasi yun lang naman talaga titingnan natin eh. Pero paano ko masasabi na siya ay ano? O ito, ano muna ang classification tong system na to? Sige. Type 0. O bakit siya naging type 0? Tama, type 0 siya. Bakit siya naging type 0? N equals 0. Ano yung tinutukoy mong M dito? Ano yung tinutukoy yung N? Dito. Yung exponent ng S. Anong tawag natin dyan? Kasi pwede tayo magkaroon ng, yung sinasabi ni Miss Tampol, pwede tayo magkaroon ng factor dito na S. Okay? Na merong exponent na N. So in this case kasi, since wala kayong nakikitang S dyan, ibig sabihin nun, yung N yung equal 0. Ayun. Yung number of pure integration sa forward path. Yun yung hinahanap natin. So yung number of factors ng S dito, okay, tells us yung number of pure integrations. Okay, kapag wala kayong pure integrations, type 0. Pag meron kayong isang pure integration, type 1. Pag meron kayong dalawang pure integration, type 2. Okay? Maliwanag? So, kaya ngayon, dahil ito ay type 0, okay? Dahil type 0 to, ang kukumputin natin ngayong static error constant para dito ay KP. Yun, yung sinasabi ko ngayon susunod doon. Pag na-identify nyo na kung anong type ng system ninyo, okay? Pag na-identify nyo na kung anong type ng system ninyo, then, ma-identify natin kung ano yung kukumputin nating static error constant. Okay? Maliwanag yun? That explains why kung bakit ang kinocompute ko dito ay KP. Okay? So, kinocompute natin dito is KP. And therefore, later on, kukompute natin yung error niya due to the step input. Okay? So, maliwanag na tayo doon. Okay, so sige. So yan rin. 0.108 yung ating error. Okay. So we may be able to verify that with a Simulink model. Okay. So pwede niyo gawin dito is i-export niyo itong model. Okay. So once na magawa niyo na to, okay, you can actually export the model as a or create a Simulink model out of this. Okay. Also, don't forget to export the tune block. Okay. I-export natin siya as CU. Okay. So check natin ito, yung model C. Okay. I-export natin sa CU for the uncompensated controller. So export natin siya. Okay. So we have that one as your okay. And then let's export this as a Simulink model. So it would ask something like, do you want to, doing so will overwrite any variable in the MATLAB workspace with the same name. So let's just let it overwrite itself. Kasi anyway, pare-pareho lang naman yan. Okay. So ayan. So we now have the following, ito yung mapoproduce sa Simulink diagram galing dun sa ating, okay, so nandiyan yung ating F, yung ating C, G, at saka H. Okay, so yung C natin dito is basically yung C na nakaset na dun sa natin, which operates on the operating point. Okay, so gawin natin is tanggalin natin itong output nito kasi hindi natin kailangan i-measure yung output. Ang kailangan natin i-measure dito is the error. So let's delete that output. And then change natin yung input natin sa step input. Okay, so we need a step input here. Okay, and then gawin natin dito. Okay, so ayan. And then we set yung step signal natin to start at 0.5. Okay. So, para medyo may 0 pa siya ng konti tapos tsaka siya mag-1 pag nag 0.5 seconds na siya. So, just click OK. And then lagyan natin ito ng signal viewer. Okay. So, para ma-measure natin yung error dito. Okay, so right click natin, create and connect viewer, Simulink, scope. Okay. So here's your signal viewer. Now, medyo i-increase ko lang tong stop time ko. Okay. Just to make sure na nasa settling, nasa steady state part na talaga ako ng response. Okay, so para masigurado lang natin, let's set this to say 50 seconds. Okay. And then let's run the simulation. Okay. So ayan. So ito yung naging results ng ating simulation, in which dito natin susukatin ngayon yung let's measure the steady state error galing dito using yung cursor measurements ng ating or yung cursor measuring tool ng ating Simulink. Okay, so click natin ito, cursor measurements, then may lalabas na options dito. So pag binila natin tong cursor na to sa part in which C na yung ating yung error signal to basically, no? Okay, so makikita niyo naman yan dito sa ating block o sa model na this viewer is actually probes the error signal. Okay, so this is the error signal. Okay, in which we are now on the steady state part ng ating error signal. Okay, and we measure it using cursor 2. So nakita natin na yung ating na-measure is 0.1085. Okay, ang na-compute natin, ang computed error natin dito ay 0.018. Okay, or kung actually yan is 0.0184. So pretty close yung ating na-compute at saka yung ating na-measure. Okay, so ayan, ito rin yan. Now, what we will do now is we will try to compensate the system, okay, by placing a compensator 0 at 0.1 at saka compensator pole sa origin. So again, that would serve as in terms ng root locus, okay, in terms ng root locus, that would serve as parang the pole would increase the system type. Okay. And then the 0 here would actually cancel yung epekto ng open loop pole dun sa ating root locus. So essentially, returning the root locus back to its original form. Okay. So we do that by going back to sa CSD app natin. So i-zoom natin siya ulit. Zoom out natin siya. And then let's add edit natin yung compensator. Okay. So dito sa compensator editor, let's add an integrator. Okay. So basically yun yung pole at the origin. Okay, that's an integrator. Okay, and then let's add so right click ulit. Let's add A0. Okay. So let's add a real 0. Okay, and let's change location. Ibigay natin yung location niya sa negative 0.1. Okay. So, press enter. So, magkakaroon tayo ng 0 doon. Okay, and take note na babalik siya sa dati niyang shape, yung root locus natin. Okay. Kaysa nung wala tong 0 na to. Okay, so babalik siya sa dating shape. And then let's bring it back dun sa ating DR line. Okay, so dali natin siya sa DR line. Okay. So, zoom pa natin. Okay, ayan. So, 0.174 yung ating target. Pero this time medyo may i-expect natin na at this point medyo may iba ng konti yung location niya as dun sa original niyang location. Okay. So now dito nakita natin na intersection natin is at negative 0.687 plus or minus J 3.84. Okay. Again, yung damping ratio natin is still 0.174. And there is a slight difference between dun sa operating point ng una, ng uncompensated system natin, tsaka dito sa compensated system natin. But nevertheless, we are essentially on the same point. Okay. So medyo pareho pa rin yung point. Okay. Pero this time, take note na yung ating compensator now has a transfer function of 158.1 times S plus 0.1 over S. Okay? So, ayun, nagbago na yung transfer function ng ating controller. Okay? And if we take a good look now at our system, okay? So, meron na siyang okay, papattern ko na lang dito. Okay, anyway, ito rin naman. Ito ay 1 ito. Okay, now this is 158.1 times, sorry. Sige, gawa lang tayo ng bagong block dito. Okay, so ito ay 1. Okay. Tapos ito ay 158.1 times S plus 0.1 divided by S. That's your C. Okay. And this is 1 over S plus 1 times S plus 2 times S plus 10. Okay. And then this is 1. Feedback natin. So, negative, positive, this is your C. Okay. Now, we take note na pag pinagsama natin ito, kasi nga this is the forward transfer function, yung combination ng dalawang. We would be able to take note na that becomes 158.1 times S plus 0.1 divided by S times S plus 1 times S plus 2 times S plus 10. Okay. Take note na ito, tumaas na yung system type niya kasi nagkaroon na siya ng pure integration. So, naging type 1 na siya. So, now we expect na kapag mineasure natin yung error nito, as pag binerify nyo ngayon using yung Simulink, okay, you will be able to see na yung error niya is actually 0. Dito sa measurement natin, basically, hindi pa siya nag-approach ng 0. Pero nakikita nyo na bababa yung error niya. Okay. So we are expecting na after some time, yung error nyo totally magiging 0. Okay. So, ayun. By the way, dito, kapag ginawa nyo to, okay, basically, i-export nyo muna yung i-export nyo muna yung compensator niyo. Okay. I-export muna natin ito. Okay, as CC. I-export natin siya as CC. Okay. So kapag nandun na siya, itong nasa natin, nasa simulate natin, ito. Palitan natin ito. Okay. Palitan natin siya ng CC. Okay. So, ayan. Ayan. So nag-CC na siya. Okay. So then we can run this. Okay. Run natin siya. And then we will have the following error signal. Okay. So again, sa mga ganitong time, hindi pa nagsisiro yung error natin. Pero as we go along, ayan, sa mga ganito, makikita natin na pababa yung error natin. Okay. So until such time na magsisiro nga siya. Okay, here's the thing. We really do not expect na completely magsisiro yung error signal natin. Okay, since these are actual system. So pag tingnan nyo talaga to sa actual, hindi talaga nagsisiro yung error nito. Okay. Pero as the fact na nakikita natin dito sa ating simulate na yung error ninyo is actually approaching 0. Okay. That means na yung papunta tayo papunta tayo sa point na nag-0 talaga yung error natin. Okay. And so yun. We were now able to design your system. Okay. So we were now able to design your system na 0 yung error. Okay. And at the same time, yung kanyang transient response performance is the same as the original. The original uncompensated. Okay, so makita natin dito ngayon na yung kulay blue represents this blue waveform represents your uncompensated system. Okay, and itong red waveform represents this is the uncompensated. And this is your compensated system. Okay. And makikita nyo na yung difference nila sa error is basically obvious. Makikita nyo na ito, yung compensated system nyo, hinahabol niya talaga na mag-1, na mag-equal sa yung kanyang final value. Okay. Whereas ito, nag-settle lang siya dun sa value niya somewhere at 0.9 siguro yun. O 0.91. Okay, mga ganun. Okay, so nag-settle na siya sa ganung value. Pero ito, hinahabol pa rin niya na mag-1 siya. Okay. Pero kung titingnan ninyo, yung peak time at saka yung overshoot ng parehong system, pareho lang. Okay, so that means na pareho yung transient response characteristics niya. Pero itong compensated system niya actually tries to reduce the error to 0. So hinahabol pa rin niya yung final value niya na maging 1. Okay, that also explains why na medyo matagal mag-0 yung error. Okay. So pag mineasure nyo rin yung pag mineasure nyo rin yung settling time nito, especially ng compensated system, makikita nyo na medyo matagal yung magiging value niya. Okay, kasi minemeasure niya yung settling time in terms ng kung kailan nito maaabot yung 98% ng final value, which is 1. Okay. Pero in that case, we should be been comparing yung settling time in terms ng original. Okay. So dito, makikita natin na at this point, nag-settle na yung system niya. More or less, dapat ng setting time din natin nandito rin. Mga around 6 seconds, 7 seconds. Okay. Dapat nandiyan yung setting time value natin. Okay. Pero pag mineasure nyo to using MATLAB, ang settling time niya, ilalagay niya sa mga ganitong value. Mga around 20 to 21 seconds. Which is hindi natin mako-compare with that of the uncompensated system. And it also doesn't mean na bumagal yung system natin. It just means na mas matagal yung or mas matagal din mini-measure yung settling time natin kasi yung settling time natin is now being measured against dun sa magiging final value niya, which is 1. Okay? So, yun, it doesn't necessarily mean na tumagal yung settling time niya or humaba yung settling time niya. Okay? So, ang parameter pa rin or ang titingnan nyo pa rin na part ng settling time dito is that when did the system actually start to try to reach for that final value of 1. And that's around this area. That's around this point. Okay. So, yun pa rin yung mas titingnan natin. Kaysa dun sa absolute measurement ng MATLAB natin ng settling time na around this at this point. Okay. So, ayun. Now, we tabulate yung performance ng system niyo. Okay. So, in this case, we were able to see na ito yung operating point niya. Okay. So, medyo magkaiba ng konti. Pero essentially, pareho lang. Now, sa other poles, sa uncompensated system, okay, since tatlo lang yung branches nun, so we expect na meron pa tayong another pole which is at negative 11.6. Okay, so, ayun. Makukuha nyo yan by kung ito yung uncompensated natin, if you put your cursor dyan sa point na yan, okay, you would be seeing na makukuha mo yung negative 11.6 na third pole. Okay. And then, on the other side, makikita natin na yung other poles natin is at negative 0.0902 at saka negative 11.6. Okay. So, malalagyan tayo ng isang pole kasi nagkaroon kayo ng isang branch. Tandaan nyo, naglagay kayo ng isang pole, isang zero. Okay, which essentially adds another branch. Okay. So, meron pa kayong isang branch, dalawang branches dito. Tapos meron pa kayong isang branch dito. So, magiging 4 na branches yan. 4 na poles ang inaasahan natin. 4 na closed loop poles. So, actually, ito dalawang to, essentially, pareho to. Itong gain natin para sa sa uncompensated system tsaka sa compensated system. Essentially, pareho yan. Yung dalawang yan. Okay. Pero syempre, may slight difference kasi may slight difference din dito. Okay. So, ayan. Now, the damping ratio is the same. Okay. Overshoot is essentially pareho din ito. Okay. Ang pinagkaiba niyan is hindi dahil sa magkaiba yung overshoot. Ang pinagkaiba niya kasi nag-iba yung yung reference value niya. Okay. Sa overshoot kasi dito, okay. Dito sa blue na line, ang overshoot nyo, naka-reference dito. So that is why mataas siya. Okay. Pero yung sa pangalawa, sa compensated system, ang overshoot nyo, naka-measure doon sa final value which is 1. Okay. Pero kung dito nyo, pareho lang naman, di ba? Okay. Pareho siya, essentially, pareho siya ng peak value. Okay. Pero, ang pinagkaiba niyan is yung reference kung saan nyo kinompute yung overshoot. Kung saan siya nag-overshoot. Again, ang overshoot ninyo is measured against the final value. Okay. So, ang formula nga nun is C max minus C final. Okay, C final over C final. Okay. Now, since nag-iba ito at saka ito, dun sa parehong case, mag-iiba rin yung value niya. Pero essentially, yung C max nyo, pareho lang. Okay, so yun ang mas titingnan natin. Yung value ng C max. Okay, so tingnan natin mabuti yun. Now, yung position constant, okay, KP, is essentially 8.22 dun sa original natin. Okay, pero this becomes 8.222 pala dun sa ating uncompensated system. Okay. So that's 8.222 and infinite na siya kasi sa compensated system kasi nga nagkaroon na tayo ng integration factor sa forward transfer function. So magiging infinite na to. Okay? So, yeah. Which means yung error nyo ngayon ma-reduce sa 0. From 0.108 magiging 0 na siya. Okay? So that's how we compare performances of the two of the uncompensated system and the compensated system. Okay. Now, how do we implement now an ideal integral compensator? In terms ng block diagram, okay, pwede nyo siyang i-implement using a parallel combination, okay, ng isang pure gain at saka ng isang integrator block. Okay, so ang nakuha kasi natin is basically 158.1 times S plus 1 divided by S. Okay. So ngayon dito meron kayong basically ito. Basically ito. Ito yan. Yan. Okay. So yung K natin dito na ginagamit to describe the game is basically ito. Okay. Pero kung igagawin nyo siya sa parallel, para makuha mo individually yung K1 tsaka yung K2. Okay. That basically, ito, i-spread out natin to. Okay. So basically, this should be 158.1 over S plus 15.81. Wala pa lang over S to. Kasi S over S, magka-cancel out sila. So 158. That is basically just 158.1. Okay. Plus 15.81 over S. Okay. So, ibig sabihin, meron kang pure gain na 158.1. Tapos, meron kang integrator gain na 15.81. Okay. So, that's how we implement it in a block. Okay. And then, later on, kung ano pa, we will be able to implement this in a circuit. So, meron tayong table na gagamitin para malaman natin kung paano natin i-translate itong transfer function na to sa isang active circuit. Okay. So that's how we design your proportional integral controller. Okay. Now, the next may question doon sa part na yun para sa proportional integral controller. Okay, so mukhang wala naman. Okay, so let's continue. Andiyan pa ba kayo? Baka mamaya wala na kayo dyan. Okay, so sige, tuloy natin. Pang-correct natin or pang-reduce natin ng error, okay, is yung tinatawag nating lag compensation. Okay, so the method by which the next method by which we so dito sa lag compensation, okay, hindi natin ma-achieve talaga yung zero error, okay. It's because we cannot implement an integrator without the use of active circuits. So kung purely passive circuits lang yung gagamitin natin, hindi tayo makakapaglagay directly ng pole sa origin. So therefore medyo iuusad natin ng konti yun from the origin. Okay. So again, ang makikita natin dito is that kung meron kang active integrator, makakapaglagay ka ng pole dito. Okay, pero this is not possible kung meron kang passive circuits lang. Okay, so medyo ilalagay natin siya ng konti dito. Tapos the principle is, medyo i-cancel natin siya using a zero na malapit sa kanya. Okay, so that is why, ang kailangan natin when we design a lag compensator is that kailangan natin mag-specify ng compensator 0 at saka ng compensator pole. Okay, now, ang requirement is that ang requirement nito is that we would like our ZC and PC, okay, to be as close as each other. Pero kailangan yung ratio nung yung ratio nung ZC over PC natin is again greater than 1. Kasi yun yung magiging improvement natin. Okay? This would be the improvement that we need, okay, in order to increase the static error constant, okay, and therefore decrease the error. Okay, so again, we say na yung ZC over PC is the improvement in the static error constant, okay, that we require. Okay, so that we would be able to increase the static error constant by this factor, okay, and therefore we would be increasing decreasing the error. We would be reducing the error by a certain factor. Okay, so kung ganun, ibig sabihin nito, dapat si pole natin dapat mababa to sa 1. Okay, so kailangan medyo malapit to ng konti sa origin. Okay, kasi dapat mababa yung value niya. Again, kung mababa yung value nito, okay, kesa dito, what would happen is that yung ratio nila would actually be greater than 1. Say for example, kung ang fold ninyo ay nasa 0.1, kasi ilalagay natin ito as nasa 1. Okay, so we will have a JC over TC ratio natin. So may improvement na tayo sa error natin. Okay, so yung pole natin, medyo malapit sa 0, malapit sa origin. Okay, tapos yung pole natin nasa 1. So nasa kaliwa siya ng compensator 0 natin. Okay, so ito, as this goes near the origin, mas malapit siya sa origin, mas mapapaliit pa natin to. Okay, so ayun. So dapat mas malaki si 0 kaysa kay pole. Okay, tapos si pole dapat mababa sa 1 at malapit siya sa origin. Yun yung requirement nung natin, nung transfer function natin dito, o nung compensator 0 at compensator pole natin. Okay, so let's have an example para natin siya, ma-appreciate natin siya. Okay, so if we have to design a lag compensator para dun sa inyong system, okay, dito sa controller niyo, using the same system na meron tayo kanina sa previous example. Okay, we will again we have evaluated the error of this system, okay, at 0.108. Okay, when the gain is 164.4, okay, and the static error constant is 8.23. Now we would like to improve this we would like to improve the steady state error. Okay, take note, ang i-improve natin is steady state error by a factor of 10. Okay, so i-improve natin si steady state error by a factor of 10. So which means, yung bago nating error, kung si error natin sa uncompensated ay 0.108, sa improved error natin o sa compensated system natin, dapat ang error natin becomes now 0.0108. Okay? So again, yan yung tenfold reduction sa error. Okay? O 10 times reduction sa error. Okay? Now, from this, we will be able to calculate the improved KP. Okay? In which we will use the formula ESS equals 1 over 1 plus KP. Okay? Tapos solve natin yung KP dito. Bibigay sa ating formula ito is this one. Okay. So, we will now have 1 minus 0.0108 over 0.108. We have 91.59. Yan dapat yung bago nyong maging maging bago nyong KP. Okay? Para ma-meet natin yung error na to. Okay. So which means from 8.23, dapat ma-increase natin yung KP natin papuntang 91.59. Okay? So yung 91.59 ay yung 8.23 natin, dapat ma-increase natin yan sa 91.59. Yung improvement na yan or yung increase na yan sa KP, dapat yan yung maging ratio sa EC over TC natin. Okay? So again, ulit. So previously, yung ating KP is 8.23. Okay? Ngayon, para ma-meet natin yung tenfold reduction sa static error, sa steady state error, ito, okay, dapat yung maging bago nating error is 0.01801. And the static error constant that would correspond to this error is 91.51. So therefore, from 8.23, dapat mag-increase yung ating static error constant papuntang 91.59. Okay? So yung ratio na yan should be the ratio ng ZC over TC natin. Okay? And that amounts to around 11.13 increase. Okay, in the static error constant. Okay, so again, pagdating sa sa position constant at saka sa error due to the step input, medyo hindi sila pareho ng improvement. Okay, hindi katulad sa velocity constant at saka sa error due to a ramp input. Pag in-increase mo ng 10 times si KV, magdi-decrease ng 10 times si error. Okay? Sa KP hindi. Dahil nga meron tayong formula na 1 over 1 plus KP. So may 1 ka dito. So which means na yung 10 times reduction sa error That means that translates to 11.13 times increase sa KP. Okay? So yung error natin na magde-decrease by 10 times would actually require you to increase your KP by 11.13. Okay? So now, so nalaman na natin na yung i-increase natin sa static error constant ay 11.13 kp. Okay. Let us arbitrarily, again, arbitrarily, kayo mamimili. Okay. So let us arbitrarily select your PC to be 0.01 or actually negative. Okay, negative 0.01. Okay. Kasi dapat nasa negative tayo para sigurado tayong stable yung system natin. So ilagay natin sa negative 0.01 yung ating PC. So therefore, yung ating yung ating CEC, mako-compute natin at negative 0.111. Okay? So ilalagay natin ngayon siya sa negative 0.111. Okay? So now, ilalagay natin yung poles at saka zeros na yan dun sa ating CST. So lagay natin siya dito. Okay? So going back dun sa root locus natin kanina, okay, originally na ang damping ratio niya ay nasa 0.174. Tapos yun yung original niya. Original na operating point niya. Okay. We now add yung dalawa nating additional pole at saka zero. So maglagay tayo ng real pole at negative 0.01. Okay. So take note na once na idagdag niyo, mababago yung shape ng root locus ninyo. Okay. And then para mabalik natin siya sa dati ngayon, dagdagan natin siya ng real zero at negative 0.111. Okay. So ayan. So we now see na babalik niya siya sa original shape niya. Okay. So we now move this towards dun sa sa DR line natin na 0.174. Okay. Okay. And take note na so by dragging again yung poles niyo papunta sa DR line niya. Okay. We find na makita natin siya ngayon sa negative 0.676 plus plus J 3.84. Okay. Tapos yung ating block now has a transfer function of 158.31. Okay. S plus 0.111 over S plus 0.01. Okay. So pwede natin i-export ito. Export natin siya sa MATLAB natin. Para mas ma-analyze pa natin yung epekto niya. Okay. So lagay natin dito as CLAG. Okay. Yeah. So ayan, ito yung CLAG natin. Okay. Now, using yung natin ito. Okay, yung ating simulink na ginagamit natin kanina. Basically, ito pa rin naman yung G. Okay. I'll now change the compensator to CLAG. Okay. Para ma-measure natin ng tama yung Okay. Remember that in this case, we are expecting na yung error natin is of this level. 0. Na-expect na natin siya na ay 0.018. Sorry. Ina-expect natin na siya ay 0.018108. Okay? 0.8. Yan. Ina-expect natin na nasa level siya na to. Okay, yung error natin. Okay. So, again, using yung ating Simulink block. Okay. So, papalitan natin siya ngayon ng CLAG. Okay. So, again, dapat pareho yung ilalagay yung pangalan niyan, system variable dyan, tsaka yung nandun sa sa MATLAB natin. Dapat pareho. Sa workspace, dapat pareho siya ng main. Okay. Otherwise, hindi yan eh. Mag-error yan. So, malalaman nyo pag nag-error yan, pag nagpula, ito. Okay, pag nagpula yan, yun. alam niyo ng may error yung system niyo or may error tong model niyo. Okay? So ayan. Now from here we run this we run this system. Okay? Then abangan natin yung results dito sa viewer natin. So from this measurement ng ating again sa cursor, I'm looking at cursor 2 kasi ito yung medyo mas settled na siya. Or mas nasa steady state na yung value ng natin. The error is 0.0122. Okay? Compare niyo yan dito sa 0.0108. So yung error na na-measure ng natin is 0.0122. Okay? So ayun, may konting discrepancy pero we're on the right track sa pag-measure ng error natin. Tsaka doon sa computed. Okay, at saka based sa naging design natin. Ayan, so medyo malapit naman yung nakukuha natin. Now, if you actually compute it, okay, pag kinumpute natin siya, yung ating error becomes, when we compute this, yung error natin becomes 158.31 times 0.111, okay, divided by 0.1 times 1 times 2 times 10. That would be our KP. Okay? So, pag kinumpute natin yan, okay, that should become 158.31 times 0.111 divided by 0.1 times 1 times 2 times 10. Yeah. So 8.78. Ang target natin KP dapat is ayun, mali pala yung ating nilagay na pole. It should have been 0.01. Okay, so this should be 0.01. Ayan. So which means off ako by a factor. Linawin ko lang kung saan ko nakuha to ha, itong formula na to. Nakuha natin, andiyan pa ba kayo? Yan. Linawin natin kung saan nakuha to ha. Dahil nga yung system niyo ay compensated na. Okay? Basically, ayun. Dahil may compensation na yung system niyo, okay, ang mangyayari sa forward transfer function niyo is ganito. Meron kayong yung compensator niyo has the transfer function 158.31, okay, times s plus 0.111, okay, divided by s plus 0.01. Ito yung para sa dito. Okay, tapos yung plant nyo, ito. Okay, so that kapag kinascade natin siya, okay, at hinanap natin yung, kasi KP is basically the limit of G as S approaches 0. Okay, so basically yung G, ito, yung buong forward transfer function nyo. Okay, so basically, ang gagawin natin dito is that lahat ng 0, lahat ng S, isiset lang natin sa 0. So that is why, pag kinumpute natin si KP, okay, pag kinumpute natin si KP, that is 158.31 times 0.111, okay, divided by 0.01 times 1, ayun, times 1, times 2, times 10. Okay, so yan yung magiging KP natin. Okay, maliwanag yun kung saan nakuha yun. Okay, medyo nagkamali lang ako nung una kasi ang nilagay ko dito is 0.1. Okay? Whereas, ang sinet nga natin itong pole na to as 0.01. Okay? So, tuloy natin siya. Factor of 10. Pag kinorek ko to, 0.1. So, lalabas yan is 87.86. 86 yung natin. Okay. So, actually ang kailangan natin para sa KP niyo is 91.59. So, may konting but we're close to there. Okay, so pag kinumpit natin completely yung error, so +1. Okay, and then inverse natin. Your error is 0.0112. Okay, 0.0112. That would be your steady state error for a step signal. Okay, so ang target natin ay 0.0108. Ito yung nakukuha natin. Okay, computed to. And yung simulate or yung measured natin galing sa simulation is around that value, 0.0122. So 0.0122 kinukuha natin sa simulation. So, nandun naman na tayo. Okay, nandun naman na yung mga values natin. Okay, and then that we were able to improve now your error by tenfold. Okay, so mas may improve nyo pa yan kapag mas maganda yung pinili yung value para sa pole. Okay. So again, pag nagde-design tayo ng lag compensator, arbitrarily, pipiliin nyo kung nasa yung pole. Okay, and choose the pole to be near the origin. Okay, then from there, compute the required location for the zero using yung improvement sa yung improvement sa static error constant. Okay, yung improvement sa static error constant, CC over PC. Okay, so this is the improvement for the static error constant. Getting static error constant. That would be the improvement for the static error constant, CC over PC natin. Okay. Then from there, so again, piliin nyo muna kung nasan yung PC. Dapat close to origin. Okay. And then from there, compute CC equals yung improvement, okay, or yung yung improvement sa static error constant, okay, times yung PC niyo. Okay, and then from there, verify niyo yung design niyo. Okay, again this improvement constant means yung ratio or yung itataas dapat ng yung itataas dapat ng static error constant niyo from the original papunta dun sa required niya. Okay? So ayun. Now there's another example here which I would like you to work on para mas ma-practice kayo. Especially sa paggamit ng MATLAB. Okay. Galing ng MATLAB para pag-i-interpret ng results ng MATLAB papunta dito. Okay, so I would like you to work on this example 8.3. Okay. So ano na lang, last reminder ko na lang. So it's likely na sa quiz ninyo, manghihingi ako ng ganitong table. Okay? So manghihingi ako ng ganitong table. Now, saan nyo siya kukunin? I would like it na pagka present nyo itong table na to, pareho nyong ipepresent yung computed ninyo at saka yung simulated ninyo. Okay? Pero at the minimum lahat ng values dyan simulated. Okay? Pero, I would really appreciate it much kasi mas, mas ebidensya yun evidence that you are, that may natutunan kayo from the past lessons. Okay? Na ipepresent nyo rin yung computed values ninyo. So, pwede nyo, di ba, may uncompensated system tsaka may compensated system dyan. Pwede nyo pang hatiin yung column na yan sa dalawa. Yung isa, computed, yung isa, simulated. So, parang lalabas yung table nyo, parang ganito siya. Dilitan natin to. Table, insert, right. So, meron pa kayong isang column dito ng uncompensated system. Okay. Uncompensated system. Tapos, lalagyan dyan, computed. Ay. Sorry. Yan. Tapos ito, uncompensated system, simulated. Okay. And of course, hindi naman lahat ng values dito merong computed na counterpart. Okay, hindi naman lahat meron diyan. At hindi rin naman lahat merong simulated. For example, itong position constant, hindi niyo naman masisimulate 'to eh. Okay? Talagang computed lang 'yan. Wala namang hindi naman natin nababasa sa MATLAB yung value ng position constant. Okay? Pero itong gain, mako-compute niyo 'yan at the same time masisimulate niyo. Okay? There is a way para ma-compute nyo itong gain. Okay? And at the same time, masisimulate nyo siya. Okay? For example, pwede kong kunin yung computed nito or yung computed nitong gain by substituting this dun sa aking original transfer function. Halimbawa, ang transfer function ko for this case is 1 over x plus 1 times x plus 2 times x plus 10. Tapos, ika-calculate ko siya using ito. Okay, so 0.694 plus 3.92i. Okay, and then, kukunin ko yung magnitude nun. So, the magnitude is ayun, yung 4.322, lagyan natin siya, 4.322 times 10 raised to negative 3. Okay? So ngayon, yung k dyan is ito. Yung 4.322 times 10 raised to negative 3, yung reciprocal niyan. Kasi di ba 1 over the magnitude of g is equal to k based dun sa dati nating lesson. So, yun. Iba yung lumabas. Okay, so baka iba lang din yung values to. But anyway, we can compute that k for that one. So, itong gain na to, nakuha ko to galing sa MATLAB. Pero there is a way para ma-compute ko yung k. Okay, so sa quiz ninyo, I would really appreciate it na magpe-present kayo ng value ng simulated at the same time, magpe-present kayo ng value ng computed. Okay? Kapag meron kayong summary table na katulad nito. Okay? At the minimum, kailangan ko yung simulated. Okay? Pero the computed values would actually provide more evidence na na-achieve niyo yung outcomes. Okay? Na nakaset dun sa mga previous lessons. Okay, so one thing is that yung paggamit nyo ng magnitude condition tsaka ng angle condition para makuha yung root locus. So isa yun sa mga learning outcomes na nakaset sa ibang lesson. Okay, so that would really be an evidence na naintindihan nyo talaga yung gawa nyo. So I would appreciate it much kapag meron kayong computed. Pero the minimum, again, kailangan ko yung simulated. Pwedeng kunin nyo lahat ng values nyo sa simulation. Okay? Naintindihan yun? Okay, so yung next lesson nito is about improving your transient response. Okay? Using via root locus. Okay? So there magde-design kayo ng proportional derivative at saka ng lead compensator. So ayun, may material naman na kayo dito. Mamaya ihabol ko yung recording para diyan. Okay, isusunod ko dun sa session natin. Okay. And then yun, para yun bukas sa quiz niyo. Okay, so hanggang dun yung quiz natin sa para bukas. Okay. Yung last lesson natin, which is improvement ng transient response at saka steady state error na magkasabay, sa finals natin sasama yan. Okay? Maliwanag? Okay. So we're over time by 2 minutes na. So I think we can dismiss na this class. Okay. Thank you for attending today's meeting and abang-abang kayo ng announcement sa quiz. Okay. So sige, dismiss na tayo. Thank you for attending.